All right, today we're going to unravel one of the greatest scientific detective stories of all time. It's a story that connects a simple falling apple to the incredible dance of the planets across the night sky. And it all kicks off with one very simple question. So let's start with a question that honestly sounds so simple you'd think a kid might ask it, but it's stumped the greatest minds for centuries. Why does an apple fall from a tree while the moon, which seems to have nothing holding it up, just stays there in the sky? What's the deal?
Okay, so to get to the bottom of this, we're not going to start by looking up at the stars. Nope. Our story actually begins right here on the ground, with some careful observations of the world right in front of us.
I mean, obviously people have always known that things fall. That's not new. But it was Galileo who really started to look at it like a true detective. He figured out that if you could just get rid of air resistance, a super heavy cannonball, and a light little feather, they'd actually accelerate downward at the exact same rate. This was a huge first clue. The force pulling things down works in a constant, predictable way.
So while Galileo's got his eyes on things falling down here on Earth, there's this whole other, much older mystery being tackled by astronomers looking up at the sky: the strange, looping paths of the planets.
For like thousands of years, everyone just went with the model from Ptolemy, the one with the Earth smack dab in the center. Then Copernicus came along and bravely suggested the sun was at the center. But the real game changer was the data, the incredibly precise lifelong observations of Tycho Brahe. And get this, he did it all without a telescope. That data was the key.
And this really shows you just how big a shift this was. The old geocentric model was, well, it was a mess. It needed all these complex circles on circles just to make the math work and explain why planets seemed to move backwards sometimes. But the heliocentric model? Way more elegant. It simplified the whole cosmic dance, suggesting there was some kind of single, underlying rule making everything tick.
This is where Tycho Brahe's assistant, Johannes Kepler, steps onto the scene. He spent 16 years, can you imagine, poring over all of Brahe's data? And what he came up with was just, wow. He boiled it all down to 3 stunningly simple and elegant laws that described how the planets moved.
First up, the law of orbits. For centuries, everyone, I'm talking from the ancient Greeks all the way to Copernicus, just assumed that anything happening in the heavens had to be in perfect circles, because, circles are perfect. But Kepler proved that wasn't right. Planets actually move in ellipses. Think of them as kind of squashed circles, with the sun not at the center, but at one of 2 special points called foci. This was a huge deal. All right, second law, the law of areas. And this one is just beautiful. It basically means a planet speeds up when it's closer to the sun, and then it slows way down when it's farther away. But here's the cool part. A line drawn from the planet to the sun sweeps out the exact same amount of area in the same amount of time, no matter where it is in its orbit.
And finally, the third law, the law of periods. This is where the pure math comes in, and it's so elegant. Kepler found this incredible connection between how long a planet takes to go around the sun, its year, or period, and its average distance from the sun. He figured out that if you square the time it takes to orbit and then divide that by the cube of its distance, you get a really, really special number. And you can see that law in action right here. Just look at the numbers for Earth and Mars. They have completely different years. They're totally different distances from the sun. But when you do the math, when you calculate t squared divided by a cubed, the answer is almost exactly the same. And it's not just them. It's the same for Venus, for Jupiter, for Saturn, you name it. This constant value was the smoking gun. It was definitive proof that there was some kind of universal rule running the whole show. So Kepler gave us the what and the how, right? He described the motion perfectly, but he couldn't explain the why. Why ellipses? Why that specific math? For that, it took another absolute giant of science, Isaac Newton, to finally crack the case. The legend, of course, is that it all started with an apple. Newton sitting there, sees an apple fall, and he starts thinking, if gravity can pull that apple from the top of a tree, well, how far out does that pull actually go? Could it go all the way to the moon? And that was the big revolutionary idea. The force that yanks an apple to the ground and the force that keeps the moon locked in orbit, stopping it from just flying off into space, they were the same force. Gravity wasn't just some local Earth thing, it was universal. And this is what led him to his universal law of gravitation. He basically said, look, every single thing in the universe with mass pulls on every other thing. And the strength of that pull, it just depends on two things: how much stuff or mass the objects have and how far apart they are. This one beautiful idea explained everything. Galileo's falling objects, all three of Kepler's laws, bam, the mystery was solved. And don't think for a second that this law, which is over 300 years old, is just some dusty old history. It is the absolute foundation of our entire space age. You see this number? 11.2 kilometers per second. That's Earth's escape speed. We get that number directly from Newton's law. It's the bare minimum speed a rocket has to hit to break free from Earth's gravity and head out to other planets. Go any slower, and you're just going to fall right back down.
And what about all those thousands of satellites zipping around up there? Their orbits are all calculated with pinpoint precision using Newton's law. We can stick geostationary satellites way up high so they match Earth's rotation, perfect for your TV signal. Or we can put satellites in low-flying polar orbits to scan the whole planet for weather forecasting and mapping. Which brings us to one last really fascinating question, and it gets to the heart of a huge misconception. We've all seen those videos of astronauts just floating around. So are they weightless because they're so far out in space that there's just no gravity?
The answer is no, not at all. In fact, at the altitude of the International Space Station, Earth's gravity is still about 90% as strong as it is right here on the surface. The real reason is so much cooler. Astronauts feel weightless because they are in a constant state of free fall. The station, the astronauts, everything inside it, it's all continuously falling toward Earth. But it's also moving sideways so incredibly fast, about 17,000 miles per hour, that it just keeps missing the planet. So it's not about an absence of gravity, it's about being in a perfect, never-ending fall.